Okay, well, thank you all for coming. I'm currently a visitor in physics here for 6 weeks, and what I'm talking about is actually the current stuff I'm working on. So necessarily a lot of it is speculative and directions that are currently being pursued, so I probably will say something wrong in the course of the talk. The group has expanded a lot since we really took off just over a year ago. We have Shurov, Albert and Patrick and Massimo, you all know. Leo Stein, you may remember, was a surf student here last year, and Stephen Pobrocki was a surf student this year. Both of at MIT now, yep. And Graham was also over here. We didn't, not at the same time as me, but we did both derive the same thing independently, which is good. Since Graham knows much more about Bayesian things than I do. So just to quickly define it, redundantly I think for the audience we have here, unmodeled burst detection, we're trying to detect gravitational waves of unknown waveform and short duration with ground-based interferometers. So that are sources that are unanticipated, poorly understood, or whose waveforms are difficult to model. Supernovae are a prime candidate, and most of the simulation results that I'll be showing you today have been done with Lazarus supernova waveforms. Basically, we can't use template searches, so we're forced to look for new and creative ways of detecting these unknown waveforms. The standard approach to date is to do excess power, but several groups are now exploring coherent burst searches. Group at Florida, using the waveburst code base. I'm not quite sure what the new code is called. It was called waveburst.net at one point in the past, but obviously that is likely to arise Microsoft's ire. The Caltech JPL ANU group that I'm a part of here with our CodeX pipeline, forked off from Q pipeline and still sharing Shurov and quite a lot of other parts of the code with the Q pipeline, and a group at Potsdam. So, this has a particularly long history for a burst search. The first significant paper in the addressing the problem was by Gersel and Barrio and Tinto in 1989, identifying the concept of a null stream, a linear combination of 3 or more gravitational wave detectors that does not contain any signal as a self-consistency requirement. Flanagan and Hughes then looked at going from a consistency requirement to actually formulating a coherent detection test in 1998. And recently, the fact that with GEO running, we actually have a global network of 3 detectors at different sites with different antenna patterns has spurred the creation of a number of new statistics by both us and the group at Florida, all owing something to the Gersel-Tinto method. So we're going to approach the problem, we're going to review first of all the Gersel-Tinto method and new statistics that have recently been proposed for it. We're then going to approach the problem from a Bayesian perspective and gain some insight on the relationship between previously proposed statistics and hopefully derive a better Bayesian statistic. And we're also going to address a problem with all of these statistics, which is that they can be fooled by instrumental glitches. They aren't as strong a consistency requirement as we might like. And we're going to propose a way to make them more robust, a way that I've just implemented and I'm just about to test, but obviously, therefore, we don't know if it actually works when we apply it to real data yet. So, a little bit of background will enable us to much more readily compare all the various statistics I'm going to be throwing at you today, and that's to work in the dominant polarization frame, which is proposed by Klemenko, and is one of a number of advances in simplifying the original formalism of Gersel-Tinto down to something much more compact than I think the original paper had. So what we're going to do is consider the whitened output of n ground-based detectors. Then for each sky position and for each frequency, we have whitened antenna patterns, which is just the antenna pattern divided through by the amplitude spectrum at that frequency. And for the n detectors, we then have a vector, an n vector of f plus, an n vector of f cross. And we can view those geometrically as directions in the space, measurement space of our 3 detectors, or more generally in our space of n detectors. So the idea for the dominant polarization frame is we use our freedom in choosing the polarization basis to pick a polarization angle such that f plus is greater than f cross, and that they're orthogonal. And once we've done that, we have the first 2 basis vectors of an orthonormal transformation we can apply to the data to give us n new streams of data from our original n detector time streams that, when combined with the appropriate time delays, produce a new basis in which the plus polarization is confined solely to the first component, cross polarization is solely confined to the second component, and the remaining components should be composed purely of noise. So there's some frowning going on in the audience, but I hope it'll become a bit clearer as we go on.
Cross,
That's the...
is that minus F plus cross F cross? Or am I visualizing a few dimensions wrong?
Look, I make no claims as to the handedness of this coordinate system.
Oh, it's left-handed.
Yeah. Well, maybe it doesn't matter. It doesn't matter. All we take is power. It doesn't matter. So, to do this, once we're in this frame, we can formulate the Gersel-Tinto test for consistency with gravitational waves very easily. The dominant polarization basis, the signal is restricted to x1, x2. So when we look at a gravitational wave coming in with some strain, h plus and h cross, in a special polarization basis, then we have just f plus going purely to the first component, f cross going to the second component. We have noise coming in, and we end up geometrically just projecting everything onto this axis. There is no signal. We've projected away the signal plane, effectively, and all we're left with is noise. That doesn't sound like a very good idea, really, but this is for a consistency test, not a gravitational wave search. So what we're interested in doing is deriving a frequentist statistic that will enable us to reject the hypothesis that a gravitational wave is present. If a gravitational wave is present, and from that direction, then by doing this transformation on the data, we will have successfully removed all trace of the gravitational wave from the x3, x4, and so on components. So they should be purely normally distributed. If we take their energy, that should be chi-squared distributed. And we have a frequentist hypothesis test that enables us to reject the proposition that a gravitational wave has come from a particular direction on the sky. And if we plot over the sky, oh dear, there's too much green in this plot, it's all gone strange. But anyway, if we plot over the sky, this is a Mollabide projection of the sky with the north and south poles and the equator here, we find that we have a lot of interesting features on this plot of the energy outside the plane of the signal if the signal came from a particular direction. Now, these are all very interesting features, but in a sense, it's quite bad that we have so much structure on this plot, because what it means is we don't have a single clear minimum where the energy is consistent with a signal from that direction. So in other words, we've rejected the hypothesis that the gravitational wave came from these directions on the sky because there's a lot of power present in the null stream, or in all these red and green places. But in all these blue places here, we failed to reject the hypothesis. So the Gersel-Tinto test hasn't done a great job of actually looking at what direction on the sky.
Is this just Gaussian noise then?
This
simulated LIGO-Virgo?
This is simulated. This is the 24-hour simulated LIGO-Virgo data set. It's the Hanford and Livingston interferometers plus, I think, a Virgo instrument that has the LIGO noise curve. So I think that's done with a time-shifted data. And the injection that we performed is a Lazarus injection at some large signal-to-noise. I think it's a signal-to-noise of 35 in there.
But the structure is not due to glitches. It's actually due to...
The structure isn't due to glitches. This is white background noise with a signal imposed on top of it. Yep. So there are a whole bunch of features on here. One of them is due to the different times of arrival. Because we're looking at taking this linear transformation of the data, mixing it all up, and then squaring it for the power, we end up with a lot of cross terms in the data. So because different directions on the sky give us different time shift, we're effectively running a correlation between two detectors. So what we expect to find is we get some junk, and then a spike when the time delay is correct, and get some more junk. And as you map that over the sky, the time delays correspond to cones on the sky, and you end up with a series of rings concentric around the baselines between the pairs of detectors. And there's 3 sets of rings visible on this map. The most obvious one is this ring here, where the 2 LIGO detectors are having the most dominant feature of the waveform line up and cancel out, lie in the signal plane, get cancelled out. And we declare that this ring on the sky is somewhere where we can't reject the signal hypothesis. And over here you see at a slightly different time shift, we've got them anti-correlated, and we can strongly reject the signal hypothesis there. there are two other sets of rings. They're much narrower rings because Virgo is much further away from the LIGO detectors than the LIGO detectors are from each other, which means that Virgo gives you much greater angular resolution on the sky for a fixed time accuracy on your baseline. So the two rings from Virgo, the two baselines, Hanford Virgo and Livingston Virgo, are obviously very close together, so you'll see these two rings that kind of interfere with each other as they slightly cross, but are more or less in the same direction. A third and final feature on the map is that there are some places where odd things happen. There are these kind of butterfly effects here, and these are the places where the global network as a whole for that particular direction is really only sensitive to one polarization. So your definition of what F cross is in the dominant polarization frame breaks down. You're basically trying to invert a matrix which is becoming ill-conditioned. At that point, your polarization frame thrashes around and you end up with a lot of rapid oscillations in there. So there are a lot of features present on that sky map, and it doesn't do as good a job of actually identifying the injection direction as we would hope. So while it correctly says that this direction is compatible with the gravitational wave, it doesn't identify it uniquely. Now, to go from a consistency test, which the Gersel-Tinto test is, to a actual search, you need to have something that's not a consistency check, something that also takes into account the presence of energy. Because the Gersel-Tinto method obviously also accepts noise. If there's just noise present in the data, then any linear combination of that data is just noise, and you'll accept that as well. So the simplest way to do that is simply perform the likelihood ratio with the noise hypothesis, that the instrument is just Gaussian. You end up with that. In log space, you've subtracted off effectively all of these terms, and you're left with the first two terms. So in other words, the terms that are guaranteed to have the gravitational wave power in them. So your transformation now is put all the gravitational wave power into two channels, and you're now going to measure the energy in those channels. And you get, unsurprisingly, a very similar map, because really this is just the total power measured by the instrument at that time minus the map I showed you earlier. So all this is the reversed colors. And here we find that the signal is preferred in these red areas, and the noise is preferred in these blue areas. But it still suffers the same problems of not being able to very well identify the direction on the sky. So these are some of the limitations of Gersel-Tinto. We have a very strong consistency requirement that there's no power in the null stream for any particular direction on the sky. But once we consider the thousands of different resolvable directions, we've ended up substantially weakening the consistency requirement. In fact, if you have a 3-detector network, there are directions that are compatible with arbitrary signals in any 1 or 2 detectors. So if you have 2 detectors, they can do anything, and they will be consistent with a gravitational wave coming from a direction that is a null sensitivity of the 3rd detector in the network. Because in that case, the null stream is just the output of that 3rd detector. So the likelihood test weakens the consistency requirement even further, because when we form the likelihood ratio, we've effectively removed the null stream from the test altogether. And the reason we've done that is because neither the signal hypothesis nor the noise hypothesis can explain energy in the x3 direction. And we're going to discuss that further. We're going to generalize the noise hypothesis to something that is glitchy, something that more accurately reflects data and reflects real data, and then we end up with a test which is both coherent and also enforces the consistency requirement. So the third point I mentioned here is that the true direction is an extremum, but globally there are many comparable extremums, so it's not a good estimator of the single direction. And the other problem is that the null stream varies wildly when the system becomes ill-conditioned, when you become insensitive to only one polarization. The Florida group call this the 2-detector paradox, and write papers about it ad nauseum. Though really it is, does not seem to be such a significant thing to me. I mean, it was an important factor in their motivation of this choice of a hard constraint, and there are various constraint likelihoods and things. But it's a simple problem, I think, if you just view it in terms of the global network becoming less and less sensitive to a second polarization and blind to a second polarization in some directions on the sky. So anyway, to address some of these shortcomings of the Gersel-Tinto test, and I've got Massimo in the audience, so I don't want to be too harsh on the Gersel-Tinto test. But there have been various changes proposed. One, Florida has, the Florida groups have come up with a couple of proposals to address the two-detector paradox and this problem where the global network becomes blind to one polarization on the sky and insensitive to that second polarization over much of the sky. One is the hard constraint, where you simply decide not to even look for any power in the second polarization. And that buys you some robustness. The soft constraint says that you weight the second polarization by the appropriate amount to make sure that you aren't giving it a full weight when you're very insensitive to it, and thus mixing in noise and mixing in the rapid changes of the direction associated with F+ as you pass through a null, as you scan over the sky. Published in this paper. A different approach, and probably a more rigorous one, was one done by Malik, which is to use Tikhonov regularization to actually take the problematic matrix corresponding to the antenna patterns as they start to go bad at bad directions, and using numerical algebra techniques to actually introduce regularizers and smooth out the problem in place. That paper sort of contains the fairly gloomy notice that, well, we can regularize the problem, but when we do that, we introduce bias, and we've got to make a careful trade-off between the bias and so forth. But one of the insights the Bayesian approach has given to us is that there is actually a very strong physical interpretation for what a Tikhonov regularizer is doing to your data analysis system. And you can make an argument that it's a very good thing indeed, not merely some sort of arbitrary numerical trick. So, the constraint likelihoods that were proposed in Florida go from the standard likelihood formulation here, the Gersel-Tinto method. If we look at then the hard constraint method, we see that we've smoothed out some of these strange points. We have fewer bright areas on the map, so we've gone a long way towards removing these unstable points and to making the maximum more unique. And if we go to the soft constraint, then we see we have a much saner looking map in place. We've eliminated these strange effects here, and we have what looks like a good global maximum at that point. So the soft constraint has definitely made a lot of progress, and we have what looks like a better statistic over the sky because of that. The Tikhonov regularization paper also makes a similar improvement, going from this system here where I think blue is good to a system here where we have much less blue and a generally smoother map on there. So these methods do work, and I think the real criticism of them is that it's not entirely clear physically what you're looking for when you're saying, I only want to look for a polarization that is the polarization the network is most sensitive to in that direction on the sky. Or that I'm making a regularization, but I'm not sure what the regularizer does physically. So, if we put that to one side for the moment and take a Bayesian approach to the data, what we want from the Bayesian approach is the posterior plausibility that a gravitational wave came from some direction on the sky, given the data that we measured. But we can only compute the probability of the data arising under a particular direction if we also assume a particular waveform, a particular type of strain present. So in classical Bayesian, so to deal with this extra nuisance parameter of what the waveform actually was, we can marginalize it away in Bayesian analysis, but to do that we are required to put some sort of prior on the strain. And we don't really have a lot of choice in this matter. If we want to keep our expression as a multivariate Gaussian, so we can do our integral nicely, which is a nice way of saying if we want to choose a conjugate prior such that our posteriors are of the same form as our priors, then we have to choose a multivariate normal distribution for our strain. If we furthermore don't want to favour F+ or F cross, because they're arbitrary choices we've made, we want it to be symmetric. So all we're left with is a single free parameter, which is the standard deviation of the strain. So in other words, we have to put into the algorithm an estimate of the characteristic scale of the signals that we expect to be able to detect. So if we put that in and grind it all together, we end up with this expression here, where this defines our multivariate Gaussian. And the interesting thing is that the use of the Gaussian strain prior automatically introduces a Tikhonov regularization term, which gives the Tikhonov regularizer a strong physical interpretation, because the Tikhonov regularizer is just the inverse of the scale of the strain that we expect to be able to detect. It turns out, in fact, if you look at the Gerstle-Tinto method, which is the limiting case when the strain prior is infinite, in other words, you have made, because you've declared yourself to be completely independent of the strain in the Gerstle-Tinto method, that's equivalent to saying I've selected a uniform, infinite, unnormalizable prior, then you end up with this expression here, which is the pseudo-inverse in here. And that is the estimate you obtain for the strain, which is the least square estimate of strain. And then if you put that back in this expression, you've made your least squares estimate of strain, you've taken the antenna pattern so to project it back into detector space, subtracted that away from what the detector actually measured, and then taken the dot product with the detector. So you've just measured the power not in strain, which is exactly what the Gerstle-Tinto method does. Now, the Tikhonov regularizer, for the case when we don't take this to infinity, minimizes both the least squares error, so it finds and the power present in the strain. So it finds the strain that doesn't fit the data best, but it also minimizes the amount of energy in the strain. So it finds the most economical strain that can well explain the data. And this does a lot towards stabilizing the Gerstle-Tinto method, because it means we don't have to postulate some enormous strain in some direction and some other enormous strain in the other polarization that happen to cancel out and produce some small effect in the data. It makes us economical with our explanations. So to go from just from the distribution for the signal hypothesis, we need to consider the alternative hypothesis of noise only, which is trivial. And once we've done that, we form the odds ratio, and we end up with this expression. You can see there we're subtracting the identity matrix from C, which also contains the identity matrix in place there. So we have a nice expression that gives us a posterior that is a multivariate Gaussian. We have normalization for it, which is pleasant, and we end up with a new statistic that we can plot over the sky. And this new statistic is a lot smoother than the one I threw up previously for the Gerstle-Tinto log likelihood. So you can see there we have the advantage of having two places on the sky where we have extrema. They have a strong physical interpretation. This is the true direction on the sky. This is the mirror image direction on the sky. And though it gets close, it doesn't rise to the level of actually being another global maxima. So the fact that the antenna patterns don't match up for this direction on the sky are enough to give us a unique and unambiguous identification of the signal that's coming from this direction. And we get some secondary maxima around the place that correspond to where the various bits and bumps.
So if we had a tetrahedral network, that antifocal point would disappear?
Yes, I think so. Or at least it would be a maximum. It would be a maximum, but it would be much weaker, I think.
Build something in Australia.
Yeah, exactly. That's why I got involved in this in the first place, is to try and build evidence for an Australian detector. And the other thing is we have nice physical interpretations for what all these other places where we get maxima are. These are all places where we've lined up the wrong peaks in the signal. So at the time, we've made the slightly wrong time shift, but we've matched up the peaks, and it doesn't work as well, but it still gives us a bit of a bump there. What we have done very successfully is get rid of these strange positions here and here, and here, where the likelihood really changes rapidly, where it starts to thrash around as our transformation to the dominant polarization system starts to go awry. So, how does this new statistic relate to other statistics? We've seen that it has a lot of the same smooth properties that you get from some of the Florida statistics. Well, when the dominant polarization frame is valid, we can express it in the dominant polarization frame like this. And so we can see in the limit as our prior over the strain goes to infinity, we go to the Gerstle-Tinto limit. This goes to 0, divide through, so all we're measuring is the power in x1 and x2. So as is common, the optimal frequentist statistic is equivalent to a flat prior. And that's something you'll come across often. So that's nice. On the other hand, we incur an infinite Occam penalty, which is another problem you typically get with frequentist statistics. And so this is the least squares strain estimate I mentioned earlier. In the other limit, where the strain goes to 0, we go to something a little bit like the soft constraint. The normalizations don't actually work out exactly. But we're getting something that would be similar to the soft constraint maps you've seen from the Florida group. Unlike the other statistics, we have a normalization term here that allows us to actually directly compare evidence at different directions on the sky, or to marginalize over the whole sky to get the evidence that there was a signal from any direction. So the Bayesian approach seems to unify and clarify a lot of the previous work. It gives us a nice physical motivation for Tikhonov regularization, gives us the same kind of smoothness that the constraint likelihoods that from Florida gave us, but without having to make strange assumptions like the only gravitational waves you will detect are the ones that come from polarizations that are the ones we can detect. Sorry, well. Okay, that's a truism, but I mean something different. In other advantages to it, the Bayesian odds ratio, this is also true of the, some of the other Florida statistics, you can actually go from a 3-detector system to a 2-detector system, which is something you can't do with the traditional Gersel-Tinto methods. So in this case, we just have Hanford and Livingston. And we can still make a not terribly bad estimate of where on the sky the detector, the signal came from. We get a ring on the sky from the lining up the peaks in the signal at the appropriate times. And we get a little bit of information about where it is more likely to lie on that ring than not by making sure the antenna patterns line up. In fact, you can even take it to the ridiculous extreme of saying where did it come from on the sky with only one instrument. And you recover exactly what you'd hope to say, which is that, well, it probably didn't come from the null directions. But otherwise we can't say much. Now, having told you about this wondrous new statistic, does it work? We don't know yet because I implemented it last week and I haven't characterized it yet. But we did have a number of characterizations done by Stephen Poprocki over the course of the summer here, where we took the standard likelihood statistic, that's the Gersel-Tinto statistic, the soft and the hard, or rather the soft and the hard Florida statistics, though the unbiased soft is the one we should be looking at because of a normalization problem in the soft. The elliptic I haven't talked about because it solves a slightly different problem, where instead of making no assumptions about the relationship between F plus and F cross, you assume it's elliptically polarized. And you can see here that there isn't a great deal of difference between the different statistics. But we would hope that the Bayesian statistic is at the top. So we're probably behaving a little bit better than the soft constraint.
Well, the standard is the old one.
Yeah, the standard one performs quite well. Total is just total energy. So that is merely making... So this, the total energy one performs worse because it's effectively having as much again energy mixed in from another noisy channel. But all of this does to some degree beg the question, they aren't making a great deal of difference and we're doing a lot of work for these different Bayesian approaches and so forth. But I think it will make a great deal of difference when we actually begin to look at examining alternative hypotheses that aren't simply Gaussian noise. And that's what I'm going to talk about next, though this is probably venturing into the more speculative part of the talk. None of the statistics...
Can I just ask a question before you go on?
Yep.
You introduced this guy sigma, right?
Yep.
You have to fix a value for that.
Yes.
You haven't done that.
No. Damn it, you noticed. There was actually a slide there where I was going to say, we think that we can set a value for sigma based on the similar kind of arguments that we make to set thresholds or to set the frequentist thresholds or set the equivalent Bayesian priors there. But yes, it is unsightly that there's a free parameter like that. We think that what you can do is make an argument whereby you look at the time you're integrating over and so forth and work out at what level the population of gravitational wave sources will start to emerge out from under the noise level. So if you take your 1 on r cubed population fall off, then at some point that will begin to emerge out from under the noise floor at some amplitude. We think that that amplitude is the amplitude you select for the characteristic scale of detectable sources, because you're not interested in the Bayesian method that says there is always a gravitational wave present, but most of the time it is so small that there is no evidence for it. So it's like that. So the signal we choose is like the signal where you decide to say, I'm only interested in detecting sources at this size or greater than it.
Does it set your false alarm, basically? Would it set your false probability?
It will have a relationship to that, but it's not exactly that. That's much more closely related to the relative signal and relative signal and noise prior plausibilities themselves. So yes, it's not something that we fully have worked out, and you're right to be unhappy about it. So yes, that's one thing we have got is we do have an additional free parameter, and that is unsightly. And we haven't fully yet worked out how to nail it down. So we have bigger problems. None of the statistics we mentioned above are actually robust against real-world noise. As I mentioned earlier, if you have a 3-detector network, you can make any measurements in any 2 detectors, and as long as the 3rd detector is well behaved, then that's consistent with the gravitational wave from an L direction of the 3rd detector. Now, I think we're the only group that's actually made an effort to invent some statistics to help us deal with this problem. And that is the so-called incoherent energy technique, which I think is in press at the moment at PRD. The idea with that is if you want to go beyond the Gersel-Tinto test, what you do is you take the Gersel-Tinto null energy, you require that the null energy be small, because that's your consistency requirement, but you also then break the null energy into two parts, one of which is composed of the autocorrelation terms between detectors, the other is composed of the cross-correlation terms. And if you're getting a gravitational wave signal, what you want to see is that there is a lot of energy in the instruments, but the correlations present between the detectors have taken you back to a null energy that makes it consistent with the gravitational wave. So this is an effort to kind of break the degeneracy and let us see into there how much energy is there, and are we suppressing a lot of energy in the act of formulating the null stream. And it seems to perform quite well. We have some fairly impressive ROC curves that say, the signal-to-noise ratio of 10, we can do a fairly good job of distinguishing between gravitational wave injections and injections of things that look very much like gravitational waves, where we inject into 3 detectors with consistent times and consistent amplitudes, we inject different waveforms. So these things have roughly the same right power and the right bands and the right time delays to be true signals. But we can still distinguish between them because of the lack of correlation between the instruments. So while that's an ad hoc method that we've characterized and seems to work quite well, it might be more fruitful in the long term to look at going beyond the normal noise model. The real problem is that whenever we perform these likelihood ratios, both the signal and the noise hypothesis predict the same distribution for power outside of the signal plane. So all the optimal tests we formulate then ignore it. Whereas the Gersel-Tinto says this is the most important thing you want to look at. This is exactly what tells you when there is something strange going on in the instrument. So we need a better alternative hypothesis that better models real noise and its ability to put power in unexpected places. So here's a speculative noise model, which is implemented at the moment, but also in the status of not yet being tested. So this is a noise model which has the advantages of being an apples-to-apples comparison with our Bayesian signal hypothesis. So just as we hypothesized that sometimes there is a gravitational wave signal that dumps unknown waveforms into the instrument from some direction on the sky, we also postulate that there is a mechanism by which glitches sometimes appear in any one of the detectors and dump in an unknown waveform and thus give us excess power. And what that tells us is we end up with going from a circular distribution to kind of a cross-space distribution that tells us if we see power along the axes of our detector space, if we see power in only 1 detector, or if we see power in only 2 detectors, then we preferentially will explain that as, well, a glitch has happened in the instrument, not a gravitational wave is present. If we see samples that put us diagonally out away from all the detector pair planes, then we will say, well, in that case, our gravitational wave hypothesis is a better explanation, a more economical explanation. So we've gone from taking our super Bayesian ellipse of expected gravitational wave power, and we've Gibbs applied our alternative noise hypothesis that says occasionally the instruments give us excess power in one instrument. Even more rarely they give us excess power in two instruments. Rarely they give us power in three instruments. And if you form then the likelihood ratio, you end up with an expression like this that says, well, we'll reward samples that occur diagonally. We'll ignore small samples. They don't provide any evidence for gravitational wave. We'll ignore samples that lie along the axes because that's only power in one instrument, and we'd be better to explain that as a glitch detection. So that is a sketch of how you might take any of the methods we talked about earlier and make them robust against real-world noise. But that is obviously a very idealized view of how glitches occur in the interferometer, so we really need to characterize that. And
how different is that from just doing a coincidence search and saying you have to see it in two detectors before I bother going on?
It's not, I guess, except in the it depends where you draw your thresholds. So yes, certainly you could do that, and it's, as with all coherent searches, you can probably make coincidence searches that probably don't exclude any useful parts of the coherent search. So yes, I think it's much the same thing. Certainly something else this enables you to do is to do optimizations where you can say, well, this never has enough power in it to get out of this region, therefore I won't even consider that time. And that's an important optimization when you're considering something as computationally intensive as, for every sample, looking at thousands of different sky directions. So, all right, so that's addressed Bayesian insights on the statistics and the issues of why we aren't robust against glitches and how we can possibly become robust against glitches. And the final thing is, all the statistics I've talked about have been effectively per time frequency pixel statistics. And something we haven't thought about very much yet is expanding our use of Bayesian ideas from the creation of these statistics to go and try and do a more complete Bayesian analysis of the problem as a whole. Because at the moment, what I'm calling a Bayesian statistic is something that's Bayesian inspired, but we then use it, we just find the maximum of it over the sky and over time and frequency, and use that as our search, which is really just using a Bayesian inspired statistic as a frequentist statistic. So can we implement Bayesian ideas in more of the pipeline? And for example, do we want to marginalize over the sky, marginalize over time and frequency? What combinations of signal hypotheses do we want to consider? At the moment, the plots I've been showing you just say that a gravitational wave dumps energy into one time pixel over all frequencies. That's our current hypothesis. Do we want to have a more general hypothesis where we have, say, 4 parameters that allow us to say, scan over the whole sky, find the rectangle that has the most power but incurs a reasonable Occam factor that is the best model for the time frequency domain the signal exists in? Or do we want to even do something more exotic like trying to find clustering algorithms? So to do that will require some rethinking of the analysis pipeline, and it also requires us to have a lot of confidence and robustness, because the ability to discard these strange things is a substitute we can have for robustness. But once you start rolling them into and integrating over them with a Bayesian analysis, you want to make sure the Bayesian analysis itself isn't tricked by glitches. Otherwise, you could accumulate weak evidence due to glitches over the sky and come up with an erroneous conclusion. So, in summary, a large number of coherent burst statistics have recently been proposed. A Bayesian approach yields a new statistic and some insight into the old ones. In a sense, the Bayesian statistic is a parameterized family of whose limits some of the previous existing statistics. A more realistic noise model might make these statistics robust against real-world noise, but that's speculative at the moment. And in the short term, we're going to concentrate on characterizing the performance of the new statistic and testing its robustness against real interferometer noise. In a few weeks, I'm still here. So, as I said, a speculative talk. Thank you for your attention. Now for the hard questions. Yeah.
Why don't you marginalize over sigma as well?
Because we can't work out how to do it analytically. So we haven't played around with that a great deal, but it doesn't appear to be any way to do it analytically. But yes, it would be good if we could.
That would be a way not to worry about
but
it.
if you assume it's the sources of these bursts have a standard candle, then
Yep.
with a population model, you could derive what sigma would be, right?
Yes.
Is that correct?
Yes, you could. The problem with that is if you do have such a population, then the vast majority of such a population will lie in the noise. So in that case, you have to make sure you're saying, I want to detect this population, but I want to detect members of this population that are of some size. And in that sense, you're back then to the original problem of saying what that size is that you want to detect. Because you don't want a thing that says, well, there is always a background of very tiny gravitational waves, because that isn't what we want to come out of the instrument. We want to say, did a silver event occur? In a sense, not a gold event, but did a silver event occur?
When we make these histograms, it triggers significant.
Yeah.
There's usually little needs and breaks in them. I think that's where you set your sigmas and your x's you whatever you use for your glitch population. You're constantly looking at those kind of plots.
Yeah. Of course, if you do look at the glitch model as well that I've talked about, it also has a bunch of free parameters, like how frequently do glitches occur, what is the characteristic scale of glitches, and all these other tunable parameters as well. And we do need to think about how to fit those to the data. Yeah. So yes, marginalization is good, but I'm not entirely sure that that doesn't introduce yet another parameter somewhere further up the stream that is still a free parameter.
Well, I mean, sigma is a scale, right?
Yeah.
You would maybe use Jeffrey spider or something.
Yeah.
Without any other parameters.
Yep. But yeah, I don't know. Albert.
How much do these cost computations? Talk about that briefly.
Quite a lot, I think. What are we still running we're still running 100 below real time
Yeah, something like that.
In MATLAB.
in MATLAB.
We're using our pipelines in MATLAB, and so rule of thumb, we can do the data analysis for any one sky position in about 1/100th of real time.
So you can do 100 pixels and keep up with the data.
Yeah, except there are something on the order of 10,000 resolvable sky directions, or a few thousand. So that's about a factor of 100 too many for us to do in real time on a single CPU.
So 100 machines,
100
keep up with the
machines.
whole sky all the time, day and night.
Day and night. But then you want to do time-like experiments as well to establish background. So
So you need a mole of machines.
something
Or a C program.
if you just train those I don't think C's going to do. C's not going to do 3 orders of magnitude.
Yeah, I hate MATLAB as much as anybody, but you know, it's not that many orders of magnitude bad.
We either need to keys to the CIP cluster, or we need enough money to hire some poor slop to recode it all for us.
Or we need to look at introducing a cutting earlier stage, and I think we could gain a lot of.
That takes you back to consistency approaches. If you've got a cut that already gives you a high confidence, you think you're seeing something.
But it wouldn't be a cut that gives you a high confidence. I think we can, if you make the cuts low enough, then you can prove that they aren't actually excluding anything. I think. But again, that's something we need to work on more.
So if you can only look at 1% of a day's worth of data per day, you can keep up.
Yeah,
So that it's a cut that just brings out that much.
exactly, yeah. I mean, there are other things too. I mean, you can cut on whether or not there was enough power present in the instrument to produce anything to get you out of that hole in the middle of the robust statistic. You can cut on saying that there was only enough, the power was only present at such times that we only need to look at this particular part of the sky that corresponds to when those excess power in the particular detectors lined up. There's all kinds of cuts you can do like that. And I don't think they will negatively impact the power of making it a coherent search as long as you set them low enough.
You looked for supernova type waveforms, but wouldn't this work for ring downs too?
It should work for anything. Yeah,
Lots of fringes in, right?
yeah, lots of fringes, but that's why you have a Bayesian analysis that can marginalize over all the fringes rather than really look for the maximum.
The ring back probably went by much filter. You would do this very similar thing with
No,
much
it's
filters.
take your cup poison. Would you rather have lots of templates or lots of pixels in this model?
There's also a related family of searches to this that are for either linearly polarized waveforms or for elliptically polarized waveforms. Patrick's been working on elliptically polarized waveforms, and they would probably be a better choice for elliptical, for for ring downs. Yep.
I was surprised how similar the 2-detector and 3-detector map looked. Am I missing something obvious?
Let's have a look.
There's more modulation along the curve.
I think that what you see here is that you get more modulation. You do get more modulation on the curve. I mean, I guess the addition. This is only one more interferometer, so you're not going to get a huge increase in signal to noise just from adding one more interferometer, but you do get a lot more localization, I think.
Is it that Hanford Livingston, seems to dominate the plot, so to speak? Is it just because they're so relatively close together that you get these fat fringes? And you're
Possibly this is.
guided by the fat fringe?
Yeah, I think it's the fat fringe.
That and the fact that somebody decided to make them really as well aligned as possible.
Right. Good point.
That's
Yeah.
what's doing. So you get so that you get strong
See, that's a good
interference.
idea.
Yeah.
Good.
That's the subject of the next commissioning break. So.
Rotating
Well, is this signal roughly equal amplitude in all three? Or is it better aligned for the two LIGO detectors?
I have no idea. This is possibly just from a random direction, in fact.
Is the signal approximately equal amplitude in all three detectors? You might have just chosen one which was poorly aligned for Virgo.
I think this one is typical, fairly typical amplitudes. I wouldn't say they're exactly equal amplitudes, but similar amplitudes, I think.
I can't do it in my head.
Are well aligned, so you tend to get very strong interference when you combine those two.
If you added Geo, what would happen? If pretended Geo had LIGO-like sensitivity.
If we added geo, then again, I don't think that would. I think what that would probably do is strengthen greatly the series of fringes we get around here. But since they're all going to be very common baselines, all right, so that would just result in more interfering fringes around the place. And I guess we would also get another very fat fringe, probably orthogonal, more or less orthogonal to LIGO Virgo ones.
How well aligned are Geo and Virgo? Does anybody know offhand?
At 45 degrees.
Yeah.
We're looking at it as past 45, but it's really bad.
Okay, so if they're 45 degrees misaligned, then we're unlikely to see a linear supernova injection like this strongly in both of them, I guess. Yeah.
So you figured out the optimal orientation for the Australian?
But so as you add more and more detectors, you get all these fringes, but they'll start to cancel everywhere except one sweet spot.
Yes.
Is that how it works?
Yeah, you're not going to get another patch of close to maximum there.
Broken up by, the fringes will break up that other intense
Yeah.
spot.
Yep. So that other spot will just go back to being just another place like this where the two different Virgo baseline fringes interfere. You'll get some structure, but it won't be a maximum. It won't even approach being a maximum. Or so we hope. Okay. No more questions? Okay, thank you.